M. Victor Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to DTH channel, lecture 5 of Astronomy and Astrophysics. This lecture is about stars, a glittering object in our night sky. Many are wondering about the formation of star, and when the stars are formed, how the stars appears as a glittering one. These are all the questions arised by many human beings in their mind. A few signs for these questions will answer by this lecture. I am going to organize this lecture in the following way: introduction, birth of a star, life cycle of a star, head-sprung Russell diagram, and finally summary of all the discussions we are going to have. We know stars are huge celestial bodies made mostly of hydrogen and helium that produce light and heat from the nuclear fusion reactions inside their cores. These stars are appearing as a glittering one in our night sky. Some stars will be more glittering, some stars will be fainter. Like that, variation in their glittering intensity will be there. Our sun is the nearest star to us. Aside from our sun, the stars we see in the sky are all light years far from Earth. You know, light year is the distance traveled by light in 1 year. So, the stars which we are seeing in the night sky are light years far from the Earth. These stars are the building blocks of galaxies. We know galaxies is made up of billions of stars, of which there are billions in the universe. Astronomers estimate that in our Milky Way galaxy alone, there are about 300 billion stars. If you look at other millions of galaxies in the universe, innumerable stars are there in the universe. The age, distribution, and composition of these stars in a galaxy trace the history, dynamics, and evolution of that galaxy. Innumerable galaxies are there in our universe. Each galaxy's evolution can be traced by knowing the age, distribution, and composition of the stars present in this galaxy. The study of the birth, life, and death of a star is the central part to the field of astronomy. Many astronomers in this world are researching stars and trying to find new stars in the universe. That's the fascinating job for many of the astronomers in this world. Now let's come to the birth of a star. For the birth of a star, this Orion Nebula is an important part. This is the picture of Orion Nebula taken by a spacecraft sent by NASA. Stars are born within the clouds of dust and scattered throughout most galaxies. So, hydrogen is the main element for the formation of stars. Those hydrogens present in the form of dust and produce a star in the universe. So, stars are born with the clouds of dust and scattered throughout most galaxies. A familiar example of such a dust cloud is Orion Nebula. This is the image of that Orion Nebula. These clouds start to shrink under their own gravity. gravity is a important invention in science. According to Newton's law of gravitation, the gravitational force of attraction between two objects is directly proportional to product of their masses and inversely proportional to square of the distance between them. This is the basic science law which governs the birth of star and the birth of universe. So the clouds present in the star start to shrink under their own gravity. As the clouds get smaller, it breaks into clumps, a group of tree-like things, a group, clumps. Each clump eventually becomes so hot and dense so that nuclear reaction begins in that clouds. Nuclear reaction will produce high temperature, especially nuclear fusion reaction requires high temperature, and due to that nuclear fusion reaction, temperatures of the order of million degrees Celsius will be ejected. So, when the temperature reaches 10 million degrees Celsius in the formation of the star, the clump which formed by the shrinking of cloud become a new star. This is a star born in the universe. Life cycle of a star. Star undergoes many life cycle as the humans undergoes childhood, adulthood, middle age, aged. Like that, human or humankind are classified based on the age. So like that, stars also classified based on their age and stage. A star's life cycle is determined by its mass. The larger its mass, the shorter its life cycle. That's the thing about life cycle of a star. Which determines the mass of a star? Star's mass is determined by the amount of matter that is available in its nebula. I told nebula is the fundamental entity for the formation of star. In that nebula, how much amount of matter available determines the mass of the star, the giant clouds of gas and dust from which it was born. As time passes, the hydrogen gas inside nebula is pulled together by gravity and begins to spin. So, nebula passes and it begins to spin. As the gas spins faster, heat will produce and becomes a protostar. That is the first stage of the life cycle of a star. We call childhood is the first stage of a humankind. No? In that way, protostar is the first stage in the life cycle of a star. Eventually, the temperature reaches 15 million degrees Celsius and nuclear fusion occurs in the clouds cores. Nuclear fusion means two atoms join together and produce a single atom. Two nucleus join together and produces a single nucleus. This is nuclear fusion. This nuclear fusion reaction takes place when the temperature of the protostar reaches 15 million degrees Celsius in the cloud's core. Now the cloud begins to glow brightly, contracts a little and becomes stable. This is the main sequence star and will remain in this stage shining for millions to billions of years to come. So from protostar stage to main stage reached by the star by this process. Our sun is in the main sequence stage right now. Sun is the nearest star in our solar system. This sun is in main sequence stage in the life cycle of a star. As the main sequence star glows for millions and billions of years, hydrogen in its core is converted into helium by nuclear fusion. Two hydrogen atoms join together means it will give a helium atom. When the hydrogen supply in the core begins to run out and the star is no longer generating heat by nuclear fusion, the core becomes unstable and contracts. Because of this contraction, the outer shell of the star which is still mostly hydrogen, starts to expand. So inner part, core part of the star starts to contract and outer part of the star starts to expand. As the outer part expands, it cools and glows red. So now the star has reached the red giant phase in its life cycle. So from protostar it reaches the main cycle. From main cycle it reaches the red giant phase. Till this red giant phase, all the stars, irrespective of their mass, will travel in the same path. After it reaches the stage of red giant phase, the star will take two different life cycle according to its mass. So this red giant phase is red because it is cooler than it was in the main sequence. After main sequence, the inner part starts to contract, outer part starts to expand. Since it expands, its temperature reduces, so the temperature of the star is lesser than the main sequence, so it starts to appear red. That's why it got the name red giant phase. And as the star expands, it becomes more big and big, so it is called giant because the outer shell has expanded outward. This is the diagram depicts the life cycle of a star. In this left hand side, you can see the formation of a star from nebula, and it goes like this. Then here it goes to supernova state. In this left hand side diagram, the star will reach white dwarf stage and black dwarf stage. Here in this right hand side life cycle, that star will reach supernova. I am going to explain that both. In the core of the red giant, helium fuses into carbon. Earlier, two hydrogen atoms joined together and helium is produced. Now, after reaching the red giant, helium fuses into carbon. All stars evolve the same way up to the red giant phase. Now, the amount of mass a star has determines which the following life cycle path it will take from there. The life cycle of a low mass star, here this is the left oval. This one is life cycle of a high mass star, is explained in that figure. These illustrations compares the different evolutionary paths low mass stars and high mass stars take after the red giant phase. For low mass stars, what happens? After the helium has fused into carbon, the core collapses again. As the core collapses, the outer layer of the stars are expelled. Earlier, before reaching the red giant phase, the stars, the inner part of the star, core part of the stars starts contracting and outer layer starts expanding. Because of that, the star appeared as a red one, and the temperature of the star reduces so that it becomes cooler. As a core, after reaching the red giant phase, as the star collapses, the outer layer of the star are expelled. A planetary nebula is formed by the outer layers. Now the core remains as a white dwarf and eventually cools to become a black dwarf. This is how stars whose mass is lesser than the mass of the sun will reach the white dwarf and black dwarf as shown in the left hand side of the diagram. This is the left hand side of the oval shape. Now 10 times or more the size of our sun. On the right of the illustration is the life cycle of a massive star whose mass is 10 times more than the size of a sun. Like low mass stars, high mass stars also born in nebula and evolve and live in the main sequence. It reaches the protostar stage, then main sequence. After main sequence, red giant. High mass stars also will reach the main sequence. After reaching the main sequence, then reaching the red giant, their life cycle starts to differ after the red giant phase. A massive star will undergo a supernova explosion. If the remaining of the explosion is 1.42, about 3 times as massive as our Sun, it will become a neutron star. If the remnant of explosion is greater than 3 times, it will become a supernova. This is how the star whose mass is greater than the mass of the Sun will become a neutron star and supernova. The core of a massive star that has more than roughly 3 times the mass of our Sun, after the explosion will do something quite different. The force of gravity overcomes the nuclear forces which keep protons and neutrons from combining. In nucleus, protons and neutrons are kept together by nuclear force. Gravity also will be there between that two, that is proton and neutron. The force of gravity overcomes the nuclear force in this stage. The core is thus swallowed by its own gravity. So, this is a common activity in the life cycle of a star. Often, star core will be consumed by its own gravity. Now, it has become a black hole which readily attracts any matter and energy that comes near it. This is how many black holes are formed in the universe. In the star itself, black hole formation takes place because of its own gravity. Once stars that are 5 times or more massive than our Sun reaches the red giant phase, their core temperature increases as carbon atoms are formed from the fusion of helium atoms. So far we have seen the life cycle of a star whose mass is 1.4 to 3 times greater than mass of our Sun. Now, life cycle of a star whose mass is 5 times or greater than the mass of our Sun, after reaching the great phase, the red giant phase, their core temperature increases as carbon atoms are formed from the fusion of helium atoms. Again, gravity continues. This gravity pulls carbon atoms together as the temperature increases, and additional fusion processes proceed, forming oxygen, nitrogen, and eventually iron. So, carbon is converted into oxygen, nitrogen, and even iron in the stars whose mass is 5 times greater than the mass of the Sun. When the core contains essentially just iron, fusion in the core ceases. No fusion process will take place in the core of the star whose mass is greater than 5 times the mass of the Sun when it reaches the red giant phase. This ceasing of fusion process in the core is because of iron present in the core, because iron is the most compact and stable of all the elements available in the universe. It takes more energy, iron takes more energy to break up the nucleus than that of any other element. So, stability reached there. Iron takes more energy to break up. Creating heavier elements through fusion of iron thus requires an input energy rather than the release of energy. So, no release of energy takes place in the life cycle of a star whose mass is greater than 5 times or more than the mass of the Sun. Since energy is no longer being radiated from the core, in less than a second, the star begins the final phase of gravitational collapse. This is the final phase of gravitational collapse. The core temperature rises to over 100 billion degrees as the iron atoms are crushed together. After reaching the red giant phase, the mass of a star whose mass is greater than 5 times or more than the mass of the Sun reaches the supernova explosion. So the repulsive force between the nuclei overcomes the force of gravity and the core recoils out from the heart of the star in a shock wave, which we see as a supernova explosion. This is how stars whose mass is greater than the mass of the sun, 5 times greater than the mass of the sun, exhibit a supernova explosion. As the shock wave encounters material in the star's outer layer, the material is heated, fusing to form new elements and radioactive isotopes. Thus, in the universe, many radioactive isotopes could be found. While many of the more common elements are made through nuclear fusion in the cores of stars, it takes the unstable conditions of the supernova explosion to form many of the heavier elements. The shock wave propels this material out into the space. The material that is exploded away from the star is now known as supernova remanent. So this is how supernova remanent is formed. So in the life cycle of a star starts with a prototype star and enters into a main sequence. From main sequence, it reaches the red giant phase. From red giant phase, 2 life cycles are produced. One is white dwarfs and black dwarfs. That white dwarf and black dwarf are produced by stars whose mass is 1.4 times to 3 times greater than the mass of the sun. Then another part is reaching the supernova explosion, supernova remanent. This is produced by stars whose mass is greater than 5 times more than mass of the sun. This is how life cycle of a star is learnt. Now coming to Hertzsprung-Russell diagram, which is an important diagram in astronomy used by astronomer to explain the history of star, formation of universe. This diagram is drawn between the magnitude of the star and temperature. Magnitude of the star and temperature. Here you can see the absolute magnitude of the star in the left hand side axis, and the top axis denotes the effective temperature in Kelvin. The bottom side bottom axis gives the special class of stars, spectral classification of stars in spectral class, then luminosity of the star, this is given here. So this Hertzsprung-Russell diagram is an important entity in astronomy to learn the life cycle of a star and the formation of universe. In this Hertzsprung-Russell diagram, one of the most important thing is it is developed independently early in the 1900s by Ejner Hertzsprung and Henry Norris Russell, 2 scientists joined together to form this diagram. It plots the temperature of stars against the luminosity. So here you can see the temperature against the luminosity. So here temperature, luminosity. Against their luminosity, this is the theoretical Hertzsprung-Russell diagram, or the colors of stars, spectral type against their absolute magnitude, the observational Hertzsprung-Russell diagram. So in this figure you can see the theoretical Hertzsprung-Russell diagram and observational Hertzsprung-Russell diagram. So color magnitude system. Depending on its initial mass of the star, every star goes through specific evolutionary stages dictated by its internal structure and how it produces energy. Each of these stages, the stage of a star, corresponds to a change in the temperature and luminosity of the star, change in the temperature and luminosity of the star, which can be seen to move to different regions on the HR diagram. So here in this HR diagram, you can see 4 different regions. To all these 4 different regions, stars moves based on their luminosity and temperature. This reveals the true power of the HR diagram, Hertzsprung-Russell diagram. Astronomers can know a star's internal structure an evolutionary stage simply by determining its position in the diagram. So they will plot the star in the HR diagram, and by knowing the position of the star in the HR diagram, they will predict the evolutionary stage of the star. That's the beauty of Hertzsprung-Russell diagram. This Hertzsprung-Russell diagram contains three main regions or evolutionary stages. The main sequence stretching from upper left corner, here you can see this is the upper left corner. This is the main sequence. To the bottom right, in that bottom right you can see cool faint stars dominates. So in the upper left corner, hot and luminous stars. Then in the bottom right you can see the cool faint stars. It's here that stars spend about 90% of their lives burning hydrogen into helium in their cores. Main sequence stars have a Morgan-Keenan luminosity class labeled 5. Red giant and supergiant stars, luminosity classes 1 through 3 occupy the region above the main sequence. So they have low surface temperatures and high luminosities, which according to the Stephen Boltzmann's law in statistics means they also have larger radii. So stars with low surface temperature, high luminosity have larger radii. So this is how that Hertzsprung-Russell diagram contributes to the evolutionary of stars. Stars enters this evolutionary stage once they have exhausted the hydrogen fuel in their cores and have started to burn helium and other heavier elements. White dwarf stars, class D stars, are the final evolutionary stage of low to intermediate mass stars and are found in the bottom left of the HR diagram. These stars, these white dwarf stars, are very hot but have low luminosities due to their small size. So the sun is found on the main sequence with a luminosity of 1 and a temperature of around 5400 Kelvin. Thus, Hertzsprung-Russell diagram helps astronomer to find its evolutionary stage. Astronomers generally use the Hertzsprung-Russell diagram to either summarize the evolution of stars or to investigate the properties of a collection of stars. In particular, by plotting a Hertzsprung-Russell diagram for either a globular or open cluster of stars, astronomers can estimate the age of the cluster from where stars appear to turn off the main sequence. This is how Hertzsprung-Russell diagram helps. So in this lecture we have seen stars are huge celestial bodies made mostly of hydrogen and helium that produce light and heat from the nuclear reactions inside their cores. Stars are born within the clouds of dust and scattered throughout most galaxies. A star's life cycle is determined by its mass. As the gas spins faster, it heats up and becomes as a protostar. The star is red because it is cooler in red giant phase. It is red because it is cooler than it was in the main sequence star stage, and it's a giant because the outer shell has expanded outward. By plotting a Hertzsprung-Russell diagram for either a globular or open cluster of stars, astronomers can estimate the age of the cluster from where stars appear to turn off the main sequence. So this is how you can learn things from this lecture. You can refer these websites to learn more about the birth and life cycle of stars. Thank you.